Hello and welcome to episode 4 in our series on information theory. In this episode, we will talk about a communication system, and more specifically, we will create a blueprint for our communication system, we will show an example of a binary symmetric channel, and we will analyze it. Our blueprint for a communication system starts with a source. It produces information and passes it to the transmitter, whose job is to send it via a channel to the receiver that further passes the information to the destination. This is the case known as a noiseless channel, where the message is unchanged across all of the steps along its way. But most often, our channel is not perfect, and there is noise acting on it. That partially corrupts our message. The job of the transmitter and the receiver is to encode and decode said information in a way that reduces the amount of corruption introduced by the noise. Let's go over an example and introduce the binary symmetric channel. Our transmitter will be sending binary digits that will be passed down to the receiver, and our channel will send our bit with a probability of p and flip it with a probability of 1 minus p. Let's say we want to transmit this sequence of bits through our channel. We just go over every bit in the input sequence and pass it into our channel. It then flips some of the bits with certain probability and sends some of the bits unchanged. We can now perform an analysis of the channel. Imagine that instead of a predetermined message, we send bit 0 with a certain probability, q, and we send 1 otherwise. Let's start by giving values to our probabilities for generating and flipping bits. When we have them, we can create a table that contains information about all possible combinations of sent and received bits. The probability of sending and receiving a value of 0 will be the probability of generating 0 multiplied by the probability of not flipping that bit. Similarly, the probability of sending 0 and receiving 1 is the probability of generating 0 times the probability of flipping a bit. And the same applies when we send 1. We can now plug in the values for p and q to get the final probabilities. Let's write out our entropy formulas. We can now place our values in the equations. I won't write out all of the equations by hand to save you some time, but I encourage everyone watching this to do this yourself for practice purposes. Here are the values that come out. Let's also bring out our nice visual representation. I will now tweak the values for both p and q. But before this happens, please pause the video and think for yourself, how will that affect all of the entropies? Do you know what to change to maximize mutual information? First, let's see what happens when we change the value for q. If we start biasing towards some value in the inputs, the entropy starts decreasing, just as expected. If we go all the way down and just send zeros, the entropy of the input goes to 0. But there is still a bit of uncertainty about the output, since the bit can get flipped. Note how the entropy of the input, given that we know the output, is also 0, since no matter if the bit is flipped or not, we can be certain that it was generated by sending a 0. When we increase the flip probability, the uncertainty of the input, given that we know the output, is decreasing. If we start flipping with a probability of half, we maximize uncertainty and get to the state where there is no mutual information. This is because we end up sending random outcomes that do not depend on our input. Similarly, When we reduce our flip probability to 0, we are absolutely certain about the input when we receive our bit, and mutual information is maximized. Here is where we will end this episode. Right now, we have all the tools needed to get to the most exciting parts of information theory. So make sure that you understand all of them and stay tuned for the next episode.